Welcome back to another episode of Thompson Hine's Environmental Laws, where we discuss current topics in environmental health and safety laws from the perspective of Thompson Hine attorneys, the regulated community, regulators, and special guests. As a reminder, LAWS stands for Land, Air, Water, and Safety. I'm Joel Eagle, a partner in Thompson Hine's Environmental Practice Group in Cleveland, and today we're going to revisit the topic of PFAS, often called forever chemicals, but from a different perspective than we have in the past. In prior episodes of Laws, we've talked about the latest developments in the fast-paced world of changing PFAS laws and regulations, including EPA's 2024 rule designating certain PFAS as CERCLA hazardous substances, EPA's 2024 rule setting drinking water levels for a number of PFAS, chemical regulations like TSCA, as well as ways for the regulated community to potentially avoid or mitigate PFAS risks. These are extremely important topics, and we'll keep covering them in future episodes. But today we'll talk about another critically important aspect of PFAS, namely testing methodologies. And I'm joined by Gwen Caviness and Kristin Robrock of Exponent, which you may have heard of, is a leading scientific and engineering consulting firm. Gwen and Kristin, welcome to the podcast. And why don't you tell us a little bit more about... Great. Why don't you tell us a little bit more about your backgrounds and in particular your PFAS experience before we get going?
Of course. Thank you. Again, I'm a health scientist in the Oakland, California office of Exponent. My expertise includes evaluating human health risks associated with exposures to a wide range of chemicals, including PFAS, both in the environment and in consumer products.
I am Kristin Robrock. I am a senior managing engineer in our Oakland office in California, just down the hallway from Gwen. I focus on environmental forensics largely and trying to help people figure out whose contamination is whose and who should pay for it. I've been at Exponent for 16 years and working on PFAS issues for about the last 5 years.
All right, so PFAS is near and dear to both of your hearts. I think at this point, most of our audience has probably heard of PFAS and know what it is, but just for the sake of clarity, why don't you refresh us? What are the basics? What are PFAS?
Sure. So PFAS, most of you have already probably heard of them. And as Joel, as you said earlier, they're nicknamed the forever chemicals. And they're reported all over the news. But just to remind everyone, the acronym PFAS is used to refer to a large number of very different chemicals, roughly 15,000 chemicals used for a myriad of different applications. In fact, there is no single definition of PFAS. So the list of chemicals included under the PFAS umbrella depends on the specific definition. But what everyone may not know is that they actually range from gases to liquids to solids. So we've all heard of PFAS liquids, which are also called fluorosurfactants, meaning that they behave like soap. And these have been used for grease and waterproofing. However, most PFAS that are used commercially and industrially are actually either gases or solids. Fluorinated gases are commonly used as refrigerants and for inhalers in the medical industry. Fluoropolymers, which are solids, are used to make nonstick cookingware, but mostly they're used to make gaskets and seals in a zillion different applications, like in automobiles, airplanes, satellites, the semiconductor, and the chemical industries. In fact, the automotive industry is one of the largest users of PFAS, and they're used in part to make cars safer, but in part to help the cars meet cleaner air emission standards. PFAS are also used to make semiconductors, which means our computers and our cell phones. So modern society relies on PFAS in so many ways, and many more than we actually realize.
Yeah, and when I've looked at the list of PFAS in products that have PFAS, it's really mind-blowing. Everything from cosmetics and automotive, and you listed a lot of them, Kristin, and it's really true. They're all over, and that's why they're not just called forever chemicals; they're called everywhere chemicals. So our modern society clearly relies on PFAS a lot. But what explains the extreme regulatory and, in some cases, litigation focus on PFAS over the past many years?
Well, the mobility and persistence of some of these PFAS, and combined with the decades of widespread use, have resulted in their being present in the environment, including in drinking water. For some of these PFAS, including PFOA and PFOS, more commonly heard in the news, animal toxicity and human epidemiological studies suggest long-term exposures to these PFAS may result in health effects. And using this information, actually, the US EPA calculated drinking water standards, what we call maximum contaminant levels, or MCLs, for PFOA and PFOS at part per trillion levels, or PPT levels. And for context, 1 part per trillion is equivalent to 1 drop of water in 20 Olympic-sized swimming pools. So these MCLs are very low. And however, for most of the many PFAS, there's little or no available toxicity or health effects information. In addition, analytical methods are not available to measure most individual PFAS compounds. In the absence of this information, some states in Europe are applying the precautionary principle to guide regulatory decisions and requirements for PFAS.
I think a lot of us have either heard of the precautionary principle or at least understand what it means. But tell us, what exactly is the precautionary principle?
Of course, the precautionary principle allows decision makers to take action when there's uncertainty about scientific evidence or a potential environmental or human health hazard. And applying the precautionary principle, decision makers may establish standards, restrictions, bans, or guidance based on the assumption that a chemical is bad and therefore poses a risk or hazard, even if the relationship between exposure and harm has not been fully established. And precautions based on this principle are relaxed only if scientific evidence demonstrates that there is no harm. Critics of this principle argue that it leads agencies, governments, and courts to make arbitrary and unpredictable decisions. It makes it difficult for courts to ensure reasonableness of agency decisions. There's also a concern that it replaces traditional cost-benefit analysis with reasoning that focuses on unproven negative effects or health effects.
So give us an example. In practice, what does the precautionary principle mean in relation to PFAS?
So there are a few examples and many ways in which the precautionary principle has been applied. So one way includes imposing bans or restrictions for all PFAS, including those that we don't know anything about. So for example, Europe, as Gwen sort of hinted at, Europe is considering restricting all PFAS in all uses, and certain US states have restricted the use of PFAS in certain applications, like for example, in food contact packaging. So California has consumer product regulations that ban the intentional addition of all PFAS, and they use a very strict definition of PFAS as a compound with a single fully fluorinated carbon. But they also regulate or limit the unintentional addition of total organic fluorine, which is assumed to be PFAS, in certain products to 100 part per million.
And Hawaii, as I said, some states have been going ahead as well with regulation, and Hawaii has recently issued guidance for assessing human health risks to total PFAS in the environment, including those PFAS that lack scientific evidence of toxicity and can't be measured using available analytical methods.
Okay, the Hawaii guidance. There's a lot of guidance out there. We've got federal EPA guidance. We've got lots of state guidance. This is another one, the Hawaii guidance. Let's talk about it. Tell us a little bit more about the Hawaii guidance and what it means for you and me and our practices.
Of course. So the Hawaii Department of Health, the HDOH, Total PFAS Risk approach requires testing using a combination of 3 analytical methods. The first is the standard EPA methods that measure individual PFAS compounds. The second is a method called the Total Oxidizable Precursor, or TOP assay, to tackle what we call precursors, or PFAS compounds that degrade to ones that we can measure. The third is the total organic fluorine analysis, and the results of these 3 tests are then combined to quantify a hazard index for total PFAS, using available tox information for non-PFAS and assuming precursors and total organic fluorine are as toxic as known PFAS.
Okay, that sounds complicated. I know from at least my own recent experience that there are all these different PFAS test methodologies, and which methodology you use can have major implications in whatever matter you're dealing with, whether that be a product stewardship case or defending a client in litigation or remediating a site. So tell us a little bit more about what is the top assay and the TOF, or the total organic fluorine method. What are those 2 methods about?
Sure. So I'm just going to take a quick step back. So analyzing for PFAS, as you mentioned, is challenging. And given that there are potentially thousands of PFAS compounds, there are multiple ways to go about analyzing them. So we have some existing EPA methods like method 537 and method 1633 that have been validated by multiple laboratories. And those analyze up to about 40 specific individual PFAS compounds. There are some third-party analytical labs that have in-house procedures, and they can analyze for up to 70 PFAS compounds. And the number of standards needed to analyze specific PFAS compounds has continued to increase. However, there are analytical challenges as you increase the number of PFAS that you test for. But ultimately, there are thousands of other PFAS compounds for which analytical methods don't exist to look at those PFAS on an individual specific basis. So we have proxy methods like the Total Oxidizable Precursor, or TOP assay, and then the Total Organic Fluorine, or TOF analysis. And those can give us some idea of whether PFAS might be present in a sample. So with regards to the TOP assay, so precursor PFAS are PFAS compounds that can degrade in the environment to what are called terminal PFAS, which, as far as we currently understand, are PFAS that can't degrade or don't readily degrade anymore. PFOA is an example of a terminal PFAS, but what we might actually use in a product is a variation on PFOA, but not PFOA itself. It's PFOA with some additional atoms attached to it. So the TOP assay is a laboratory method that forces this degradation of precursors down to the terminal PFAS, so then we can detect them using the traditional EPA methods like 537 or 1633. And so it forces the degradation of that, say, PFOA variation on the theme down to actually PFOA. And so the TOP assay is a helpful tool to get a rough idea of how much precursor mass is present that, for example, you might need to design for when implementing a remediation system. However, this method doesn't tell us what the original precursor compound was. On the other end, we have total organic fluorine, which is a completely different method, and that analyzes for the presence of fluorine atoms that are attached to carbon atoms. And this method is a relatively cheap and easy way to screen for PFAS. However, depending on which total organic fluorine method you use, and there are a few options, and exactly what you're looking for, results may vary. So ultimately, you have to be careful with interpreting total organic fluorine results because they may not actually represent PFAS.
So you've got these proxy methods, and in an ideal world, you'd just be able to do a test and figure out, of all the, say, 15,000 PFAS that exist, and maybe there are more, you could just know what PFAS you're dealing with. But that's not the world we live in right now. So we have these proxy methods to help us out. Are there any problems with using these proxy methods?
Yes, for sure. So, for example, with the total organic fluorine methods, we have no idea what we are actually what we're detecting. You know, the fluorinated compound that we're detecting is actually a PFAS. There are many fluorinated pesticides and pharmaceuticals that can be picked up by these methods. In fact, there was a recent paper that came out about 2 weeks ago that found that 75% of the fluorinated mass in municipal wastewater that arrives at wastewater treatment plants actually comes from fluorinated pharmaceuticals, which we don't typically consider to be a traditional PFAS compound. And so just because it's fluorinated doesn't mean it's a PFAS.
All right, there are, if I'm getting this right, there are a lot of different types of PFAS. We don't know the toxicity of all the different types of PFAS. We can't test for all the different types of PFAS. And in short, not all PFAS are the same, which I think is a really important point that I see mistakenly made just talking about PFAS as if it's a single chemical that we can evaluate or regulate as a single chemical, which is not the case. The TOF method seems to be fraught with risks in drawing definitive conclusions about what actual PFAS might be in a sample. And I think it's fair to say you and I, the three of us, are not alone in thinking this. So some courts have recently been confronted with this situation, and there are recent decisions that are in line with that. So for example, in the fall of 2024, a federal court in your state of California dismissed in part a consumer class action, finding that plaintiffs' total organic fluorine testing was insufficient to demonstrate that defendants' products actually contained PFAS. The plaintiffs had alleged that defendants' pure cotton tampons contained PFAS and that pure cotton was a false advertising. Basically a greenwashing claim that pure would indicate that there shouldn't be chemicals like PFAS in them. Plaintiffs based the allegation on total organic fluorine, which it claimed was the gold standard. That's a direct quote from the plaintiffs for determining the presence of PFAS in a sample, and that finding TOF is indicative of the presence of PFAS. But the court disagreed. The court found that the inference that TOF in a product means that the product contains PFAS to be, quote, not plausible, and went on to say that targeted PFAS analyses are necessary to demonstrate that, quote, the total fluorine measured originally comes from the use of PFAS. So I'm sure that there were experts that identified those issues, and the court came to that conclusion. There are several cases in 2024 that came to a similar conclusion. Which is just a really important point to keep in mind going forward into the future, understanding what test methodologies you're using, having really good experts to guide you through the process. Kristin, does the Hawaii guidance potentially lead to a similar overestimation of PFAS? Or Gwen, you want to take that one?
Well, of course. So the problem with the Hawaii total PFAS risk approach is just what you're talking about. That it may overpredict risk because it assumes that all of the total organic fluorine in the result is PFAS, and that the toxicity of PFAS, for which we don't have any information, is the same as that of known PFAS. And another problem is that assuming all of the PFAS are equally bad could cause us to spend enormous sums of money to clean up something that may have much less risk associated with it than we're assuming.
How much money are we talking about here? Enormous sums? Are we talking millions, lots of millions, billions?
I would say we're in the order of billions. So just as one example that we can discuss is that the American Water Works Association recently sued the EPA for not accounting for the full cost of PFAS treatment when the EPA developed the new maximum contaminant levels, or MCLs, for drinking water, early last year. And so when developing an MCL, the EPA must consider cost and feasibility and not just calculate a number based on toxicity. And then the EPA must determine whether the health benefits associated with achieving the MCL outweigh the cost of treatment to meet the MCL. And so in that lawsuit, the American Water Works Association claimed that the cost to implement PFAS treatment in drinking water plants are approximately 2.7 to 3.5 billion per year, which is almost twice what the EPA estimated of $1.5 billion per year. So that's just the cost of treating drinking water and not even actually cleaning up contamination.
Right. And we know there are sites all over the country, dozens, hundreds of sites where PFAS have been detected, maybe detected at high levels. So we've got lots of different categories where PFAS costs are going to be at this really high level going into the future.
So Joel, you've been asking us some questions. We have some, or at least one for you. Yesterday was a change in the administration, and we were just wondering, do you expect the new administration to change how PFAS are addressed in the United States moving forward?
Well, I think that's the billion-dollar question that everybody's asking right now. It's hard, and given that President Trump has been in office now for 26, 27 hours, it's early to tell. But there are some indications that the federal approach to PFAS might change. We know that President Trump has stated that he is not involved, did not sign off on Project 2025, but to the extent the administration seeks to apply aspects of Project 2025, PFAS would certainly be implicated. In fact, Project 25 specifically calls for the revisiting of the CERCLA hazardous substance rule that designated PFOS and PFOA as CERCLA hazardous substances. And right now, that rule is being challenged in federal court, as is the 2024 rule setting the drinking water standards for several PFAS that you both have mentioned today. President Trump has also made it really clear that he will focus on a deregulatory agenda, which could lead to impact EPA's efforts regarding PFAS. But remember that we're talking, that's the federal level. Remember that states have a key role to play here, and we've seen that play out in the past regarding PFAS. Many states have taken action of their own, often in advance of any federal action to address PFAS. Drinking water standards, remediation standards, chemical regulation, product regulations. We have a lot of states that have and are going to continue to lead the way. And going forward in the Trump administration could continue to fill in gaps that the federal regulations might leave behind. But the problem here is that this unfortunately leads to quite a patchwork of PFAS regulation that already exists and is or will likely only get worse in the next 4 years, which emphasizes the need to look closely at what state or states your issue may implicate. I at Thompson Hine, and I know you all at Exponent, will be following all of this in 2025 and the next 4 years. So I think we should probably start planning our next podcast episode where we can cover some of these changes. But with that, I'm going to end the podcast for the day. Gwen, Kristin, thank you so much for joining me today and sharing your expertise and thoughts.
Thank you.
Thank you. It's been a pleasure.
Very much.
All right. Well, this concludes another episode of Thompson Hine's Environmental Laws podcast. If you have a request regarding a topic you'd like to hear in a future episode, please send an email with your request to me at joel.eagle@thompsonhine.com. And we'll see you again soon. Thanks so much.